webinars are made possible thanks to generous donor support. If you'd like to contribute, please visit our website, autism.org.
I'd like to welcome everyone to the first webinar co-sponsored by the Autism Research Institute and the World Autism Organization. In order to provide the best guidance and support to those on the autism spectrum and their family members, we need to work together since everyone brings something unique and special to the table. The needs of the autism community worldwide are great, and no one organization can provide the needed help for everyone on the entire autism spectrum. Let me tell you a little bit about the Autism Research Institute, or ARI. Afterward, Paul Shattuck will describe some of the work of the World Autism Organization. Now, ARI is the oldest autism organization in the field. We were established in 1967. That's 54 years ago. The founder, Dr. Bernard Remland, is credited with changing the autism field. When he first heard about autism when trying to help his son, Mark, he realized that the entire professional community was blaming him and his wife for causing autism. After reading literally every paper ever published on autism, he argued rather convincingly in a book in 1964 that autism is a biological condition and not due to emotional neglect by parents. Dr. Remland was also instrumental in supporting the early work on ABA, or applied behavior analysis, sensory interventions, nutrition, restricted diets, and biomedical interventions. As far as other things that ARI is working on these days, ARI sponsors and co-sponsors webinars. We also offer continuing education credit for physicians. We organize national and regional think tanks. We fund research on the causes and effective treatments, and we also conduct research on our own. We publish books, a science quarterly newsletter, and e-newsletters, and we help distribute research findings to support groups worldwide. We are honored today to have Dr. Manuel Casanova present a talk on transcranial magnetic stimulation, or TMS. Dr. Casanova has pioneered this treatment, and there's a great deal of research to support its effectiveness. Dr. Casanova is one of the leading scientists in the field of autism, and he has published important research studies as well as shared his expert opinion on many different topics. He is also a close colleague and a very good friend of mine. Thanks in advance, Manny, for helping us inform the autism community about TMS. I should also mention this webinar is being recorded, and playback will be online later this week at www.autismwebinars.org. Free certificates of participation are available upon successful completion of a brief knowledge quiz about the webinar. The quiz link will be on the playback page immediately after the talk. The link to the reminder email was sent earlier this morning. So thank you all for attending. And Paul Shattuck, could you say a few words?
Right. Good morning, good afternoon, good evening, wherever you are. It's 5 o'clock in the evening here, but I'll say good day and cover the lot of you. Anyway, thank you very much for attending this meeting. A novel experience for us all, I think. I'm the parent of a young man with autism called Jamie. He's 50 years of age now, and I haven't seen him for a year and a half because of COVID. He survives on a farm in Ireland, and of course, because of COVID, we cannot go there. And even if we did, we couldn't see him. But I keep in touch. But when Jamie was born in 1970, He was diagnosed in 1974. And then soon after that, I realized that the professionals in England didn't know a great deal. And I sort of thought, this is rubbish that I'm being told. So I heard about this quack in San Diego called Bernard Rimland. So I phoned him and realized immediately, this man is talking sense. This is the direction that we should be looking at. Now, as a parent, I feel that all the parents throughout the world of people with autism, we sort of know each other. We are brothers and sisters. The problems are the same and the solutions are the same. So a lot of us came together to try and form a world organization where we can all get together, and those who have experience and knowledge can share it, can give it free of charge to those who don't have it. That is the only way we're going to make progress. We think that all children and adults are born equal and they should have these equal opportunities. And that was one of the reasons why the World Autism Organization was set up. I had a history in Autism Europe, but we could not make registrations or anything with the World Health Organization or the United Nations. We had to be world before they listened to us. So that is why we did it. It was a lot more difficult than we thought it was going to be. Just living in Europe, you can fly from one country to another and see each other. But on a world scale, that is not possible. We did meet each other at big conventions, at congresses, but I have a feeling that the days of the big congress are over now. Parents cannot afford to travel and schools cannot afford to send their staff to visit them. So we have to find other ways. Smaller events, webinars like this are perfect, or a combination of the two seem to be the future. The motto, if you like, the reason for existing of the World Autism Organization remains as it was from the first day: to improve the quality of life for people with autism and their families throughout the world. We did not appreciate how difficult that was going to be, but we've been walking more for the last 22 years, trying to make progress. We have people from many countries in our organization. On our Council of Administration, there are people from 12 countries. Our president is Samira, who is from Kuwait, and we have representatives from all around the world. So we have to meet regularly on an internet basis, and it's not easy. I want to mention briefly, we had a Congress in Houston in 2018. On one level, the financial level, it was disastrous for us. We did not attract the crowds we thought we were going to. But on other levels, everybody enjoyed it. There were some fabulous speakers. And amongst them, I must mention the people with autism who spoke. I did not know most of them had autism before we accepted them, but they were brilliant. Each of them was brilliant. I was expecting trouble because of the moves that some people don't all believe the same approaches are appropriate to people. And so I was expecting trouble, got none. And everybody worked together. It was a very happy event in the end. But I think for me, it was a big thing to see 20 people with autism speaking as professionals. They didn't write, "I am autistic, may I speak?" They just said what they did, and they behaved beautifully, and their presentations were most illuminating. It was an important event for that reason. Now, can I suggest you go to our website? Steve has mentioned one website. I will mention the website for the World Autism Organization. It is just www.worldautismorganization.com. www.worldautismorganization.com. Now, for many of you who are not Europeans, you don't know how to spell organization. It's not a Z or a Z in the middle, it's an S. So it has to be organisation with an S if you want to see anything. We often have problems with spell checkers converting it as when people try to speak to us as well. But you will see what we're up to there. And if you wish to join us in our work, for a full national society, it's €150, which is not that different from $150, or €15 only for an individual who wishes to join. So there's no reason why you can't pay up that money and send it to, or pay it through PayPal or through our bank account. Anyway, I mentioned the difficulty we have in the autism movement. Our weakness is that we don't agree on things. Getting people with parents to agree, and people with autism as well, is like herding cats. They don't agree. It's impossible to get everybody together. But our big problem is that we've not been able to speak with one voice. Everybody has their own ideas about what should be done, but we will not get any developments worthwhile until we do speak with one voice. Like in a football crowd, one person, you don't hear them. But when there's 50, 60,000 shouting the same thing, oh yes, you hear them. And that's what we've got to do, agree on these things. Anyway, the one voice you're going to hear next is that of one of our great friends and heroes, Manuel Casanova, who's known throughout the world, and we're very honoured that he is here to speak at our first event. He's a gentleman, he's a good guy, and I'll say no more about him, but ask him to speak on transcranial magnetic stimulation in autism. Thank you.
Well, thank you very much for that kind introduction. Good afternoon or evening, as the case may be. I am very pleased to be here with all of you and to be able to share this presentation titled Transcranial Magnetic Stimulation, or TMS, in autism. This is going to be a review of some of the research conducted mainly in my laboratory and the translational efforts we have made using this technique in clinical trials. Is there a scientific basis for using TMS in autism? What is TMS? What have been the preliminary results of these studies? Stay tuned with me, and sometime during this lecture, I will try to answer these questions. But before I begin, I would like, first of all, to express my gratitude for the invitation that made this conference possible. To Steve Edelson, Executive Director of the Autism Research Institute, and Paul Shattuck, who has been the perennial representative of the World Autism Organization. I truly praise the efforts of your organizations aimed at providing educational programs and advocacy worldwide. I also appreciate the interest of all the patients, autistic individuals, and healthcare providers that are joining us. It is your interest and support that has always motivated me in my autism research. Several years ago, Declan Murphy, a professor of psychiatry at King's College in London, he gave the plenary lecture for the International Society for Autism Research. The theme of his lecture was the lack of proper treatments in autism. In reviewing the medical literature on available therapies in autism, Declan found an absence of curative treatments. Rather, all of the treatments were symptomatic in nature. In other words, all of the therapies that he reviewed for autism were supportive, targeting some of the symptoms, but not the underlying cause. In this regard, therapies were aimed at increasing patient comfort and improving their quality of life. But at the end of the day, week and month, the patients would remain with the same predisposition to the symptoms that brought them to the physician in the first place. Declan concluded his lecture by saying that unless treatments focus on the cause of autism, on its pathology, there could never be the possibility of curative treatments. In this sense, we will have to provide a small review of those pathological findings that have been reported in the brains of autistic individuals in order to determine if any of them can serve as a target for possible intervention. It should be remembered that autism is known as a neurodevelopmental disorder. And as such, the development of the nervous system is affected, thus causing the symptoms of autism. Therefore, before we talk about changes in the brains of autistic individuals, we will have to take a little bit of a detour and talk about brain development. Theodor Hermann Meinert was an Austrian psychiatrist, neuropathologist, and neuroanatomist of the 1800s who maintained the belief that disorders of brain development were responsible or could provide a risk factor to psychiatric disorders. At the time, Meinert didn't know much about brain development. He said that brain development was similar to a complex ballet where the performers were the neurons. Fortunately, we have learned a lot more about brain development, especially in recent decades of research. During the formation of the cerebral cortex, those cells that are progenitors of neurons migrate from a periventricular location labeled on this slide as the periventricular germinal zone to their final destination within the cortical plate. The migration of these precursor cells is called radial or tangential, depending on the orientation these cells take during migration with respect to the surface of the developing nervous system. Cell division within the periventricular germinal zone begins before the 6th week of gestation. At that time, neuroblasts, or the precursor cells of neurons that migrate to the cortical plate, do so along glial fibers that are radially arranged, and when they reach their destination, they detach along multiple layers. Those arriving earlier break off in the deeper layers of the cortex. And by that, I mean those closest to the white matter. Alternatively, the migratory cells that arrive later on, they break off in progressively shallower locations or closer to the surface of the brain. Interneurons, or inhibitory cells, arise mainly from the medial and caudal eminences and migrate tangentially to reach their final destination in the cortical plate. These inhibitory neurons are first established in the lower cortical layers and mature along ascending layers next to the pyramidal cells with which they establish contacts. The distance traveled by the neuroblasts that migrate tangentially is much greater than that traveled by the precursor cells that follow the radial pathway. In this way, tangential migration allows future interneurons to reach destinations far removed from their origin sites. This route, that we could call tortuous, expands the window of opportunity or time during which the migration of neuroblasts may be disturbed. In autism, the presence of malformative lesions, like clumps of gray matter located where they should not be, so-called heterotopias, in conjunction with an increase in cell density at the junction of the gray-white matter substance, illustrated here to the right of this figure. The presence of a minicolumnopathy, as well as the presence of focal cortical malformations, all suggest a neuronal migration disorder. Abnormalities of cell division and subsequent migration are common in autism spectrum disorders, or ASD. In fact, I have to point out that in recent series using full brain sections along all of the rostrocaudal axis of the brain, Jerzy Weigel and colleagues reported the presence of these neuropathological markers in 92% of the autopsy cases they studied. The malformative or dysplastic changes are frequent enough for some researchers to propose their use in subtyping or stratifying ASD patients. The confluence of tangential and radial migratory currents into the cortical plane results in a series of cellular associations characterized by functional dyads between neurons that are excitatory, better known as pyramidal cells, and those that are inhibitory, so-called interneurons. The overlap and interdependence of these cellular dyads, stacked one on top of each other, results in a unit of anatomy and function called the minicolumn. Raphael Lorente-Deneau was the first person to discern the functional role of these vertical cylinders when they stated that all the elements of the cortex are represented in them, and therefore can be called an elemental unit in which theoretically the whole process of transmitting impulses from the afferent fiber to the efferent one can be achieved. Minicolumns are thought to contain a canonical circuit that repeats along the cerebral cortex, thus providing a basic similarity of design and function. In the next slides, I will talk about how these modules or minicolumns are structurally and functionally abnormal in autism, and how these results gave rise to the use of transcranial magnetic stimulation in this spectrum of disorders. Postmortem studies of minicolumnar morphometry in autism indicate noticeable differences compared to neurotypicals. These studies indicate compartmentalization of minicolumns with a significant reduction in area in the peripheral neuropil space. This is illustrated in this figure under the abbreviation NS. By way of contrast, its central compartment is relatively preserved. The periphery of the minicolumn is populated by inhibitory cells that help establish the so-called lateral or surround inhibition. Now, I will have to emphasize this point, which is very important, that the periphery of the minicolumn is populated by inhibitory cells that help establish lateral or surround inhibition. Mountcastle described this compartment as giving the minicolumn a strong vertical flow of inhibition. Peripheral neuropil abnormalities in autism therefore suggest an inhibitory deficit. It is therefore logical to think that in autism, the inhibitory cells that occupy this space at the periphery of the minicolumns are diminished in number and or function. And in addition, that correcting this inhibitory deficit could therefore provide a therapeutic target in autism. In future slides, we will show how we targeted this inhibitory deficit with transcranial magnetic stimulation. Having an idea similar to Mountcastle, who proposed the strong vertical inhibition flow at the periphery of the mini-columns, Sethen Gothai and Arbib described the function of the peripheral mini-columnar compartment as a shower curtain of inhibition. In autism, a faulty shower curtain of inhibition, talking about a decreased peripheral neuropil space in mini-columns, allows stimulation to spread from one mini-column to adjacent mini-columns. The end result is to decrease the signal-to-noise bias of the cerebral cortex and to create a cascade of excitation that could provide an explanation to the sensory problems and seizures often observed in autism. In the illustration, we emphasize how a shower curtain normally keeps the water inside of the bathtub. If it is defective, the water splashes the floor outside of the bathtub. Similarly, when the mini-column shower curtain of inhibition is defective, as in the case of autism, the signals that are conducted in the center of the mini-columns are disseminated to the adjacent mini-columns, thus creating a cascade of excitation. Information contrast is thus diminished, and often small signals that could have been construed as noise, they tend to overpower the system. One analogy that can help us understand the proposed deficit of inhibition in autism is to imagine a bundle of copper wires conducting electricity. Each cable is isolated from its neighbors by a non-conductive or insulating material. If this insulation is defective, copper wires could touch each other to create an alternate path for the electricity to flow in. In the worst case scenario, when the alternate path is one of much lower resistance, the same could cause a short circuit. The short circuit is an unintended route that detracts from the normal operation of the circuit and, in some cases, can even damage it. The short circuit provides a preferential pathway that overrides anything else that may be happening in the system. In the case of autism, noise or an unintended signal may in this way overpower the processing capacity of the cortex. This slide provides the results of a computer modeling study from my research group. This effort was aimed at trying to visualize the lateral inhibition of mini-columns by plotting the net effect of the activation of one of these modules based on the tangential distance to the cortical surface. When an idealized and healthy mini-column is active, its short-range output is a combination of excitatory signals, illustrated here with the red color, and inhibition, illustrated here with the blue color. Together, they create the profile of a Mexican hat model of excitation inhibition. This is what is expected normally. Pathological mini-columns, those where an inhibitory deficit procreate a cascade of excitation. One where the activation of any one tends to activate a whole set of mini-columns, results in a profile of a top hat. This is what happens in autism. In a neurotypical individual, information processing results in a profile having multiple values, the Mexican hat model. While in autism, much of the information ingrained in the variability of excitation is lost, thus resulting in a digital or binary system with two possible states, excited or inhibited, the top hat model in autism. You could say that the brain of many autistic individuals seems to be wired as a switch going immediately from on to off and vice versa, with little mediated in-between states. On the right side of the slide, you can see how neurons react to particular stimuli. In this case, a neuron that recognizes a square wave becomes activated and increases its firing frequency. Even in the presence of a low background of noise, the pulse pattern is clearly visible. In a noisy background, however, as in autism, the original pattern is lost or more difficult to recognize. Currently, both electroencephalogram or EEG and tactile processing studies indicate lateral inhibition abnormalities in individuals with ASD. In ASD, several lines of evidence suggest the presence of a cortical inhibitory deficit. Postmortem studies in ASD have shown a reduction of GABA inhibitory receptor in the cerebral cortex. Moreover, immunocytochemical studies have located this inhibitory deficit in a subset of inhibitory cells containing a calcium-binding protein called parvalbumin, usually abbreviated as PD. John Faraday is an associate clinical professor of psychiatry at Harvard Medical School and an internationally recognized expert in the field of neuropsychiatry. Among some of his writings, he has tried to describe what could happen to an individual whose brain is bombarded by excessive stimuli. The relevant example being provided by the deficit in the shower curtain of inhibition previously described in autism. He says the following. Number one, what the researchers found is that, in fact, the overload of stimuli is devastating for the brain, for the ability of oneself to maintain its cognitive functions. Entirely normal people who are severely overloaded, especially by unpredictable and uncontrollable stimuli, may show poor functioning, high physiological stress, internal chaos. Those people take impulsive actions and maintain a lower level of adaptation to life's challenges. This is something that certainly incapacitates the individual, limiting the way in which a person thus affected can react and adapt to his or her environment. And second, John says that because research shows that prolonged states of sensory overload or noise are actually traumatizing, we can conclude that patients with severe mental disorders are actually being traumatized by their own brains. This point underscores how essential it is in these cases to offer treatment as soon as possible. In essence, the earlier the treatment, the better the prognosis. Cell destination specification studies have shown how interneurons develop in an abundance of cells that vary among each other in terms of their morphology, neurochemistry, and electrophysiology. In neuropathology, the subtyping of interneurons has been done using surface markers, that is, calcium-binding proteins. When comparing brain tissue samples from autistic individuals and neurotypical subjects, an immunocytochemistry study by Veronica Martinez-Cerdeño revealed a significant reduction in the total number of parvalbumin PB-positive cells in all areas and cortical laminas examined. These cells are indicated in this slide as dots with a magenta color. Positive PB cells account for approximately 40% of all interneurons and include chandelier and basket cells. This is of clinical importance, as the function of these PV positive cells is significantly diminished in the prefrontal cortex of numerous psychiatric conditions. Among them, it is worth mentioning schizophrenia, Alzheimer's disease, and bipolar disorder. I should also point out that there are animal models of autism showing a correlation between decreased PV expression and the behavioral deficits characteristics of the ASD phenotype. This clinical pathological correlation makes me believe that a loss of PV positive cells is a true core feature of autism and a possible target for therapeutic intervention. As I said in the previous slide, immunocytochemical studies by Veronica Martinez-Cerdeño have shown a significant reduction in the total number of PV positive cells in all cortical areas examined from individuals with ASD. The neuropathological finding is of great significance. And for that reason, we will expand a little bit more on it, especially in regards to how this pathological finding relates to a particular bandwidth of brainwave oscillations called gamma. Rapid inhibition by PV positive cells helps regulate the activity of pyramidal cells, preventing uncontrolled arousal, refined receptive fields, and synchronize the firing rhythm of neural populations responsible for gamma oscillations. Among neurons that are PV positive, basket cells are highly interconnected through chemical synapses and gap junctions. The network formed by these cells results in a synchronous triggering manifested as high-frequency gamma oscillations. It is worth emphasizing some of what we have learned so far before moving ahead. A pathological increase in gamma oscillatory activity, as noted in autism, reflects an imbalance in the homeostasis of excitatory and inhibitory cells within the cerebral cortex. This inhibitory deficit, like gamma oscillations, may be the result of a decrease in PV positive cells. In the following slides, we will show how we can target this deficit using TMS. Synchronous recruitment of PV positive interneurons generates, as we have already said, gamma oscillatory rhythms that arise during the execution of cognitive tasks, especially those functions referred to as executive functions. These are functions that allow us to associate ideas, movements, and actions to perform more complex tasks. 2 points of importance that I will underline and which appear in this slide. One, modulation of gamma oscillations has been associated with cognitive performance, particularly when stimulation is carried out over the dorsolateral prefrontal cortex. And second, therapy with TMS, transcranial magnetic stimulation over this area of the cortex, can normalize the abnormalities of gamma oscillations. These two observations gave us the idea, in part, of using TMS over the prefrontal area of the brain as a possible therapy for ASD, and of using gamma oscillations in conjunction with other behavioral examinations as outcome measures. I will now like to take a brief detour in order to expand on the clinical implications of gamma oscillations in autism. These oscillations are the ones that allow us to associate different elements of our perception into a whole. Temple Grandin, a well-known autistic individual, has said that she has trouble trying to accept how a Chihuahua and a Dalmatian belong to the same classification of animals, both of them being dogs. In autism, as we have already said, gamma oscillations are abnormal. These are the oscillations that allow us to put objects of our environment in context, such as the Chihuahua and Dalmatian in the case of Temple Grandin. These oscillations are the ones that help us generate a whole or gestalt out of an experience, to recognize a face as one belonging to that of a friend, and not to a detached set of eyes, nose, and mouth. Gamma oscillations therefore help us to have an adequate perception of reality and to take appropriate actions. Again, I emphasize that these oscillations are abnormal in autism and could serve as an excellent outcome measure when judging the efficacy of an intervention like TMS. The analysis of electroencephalographic recordings allows the identification of bands of brainwave frequencies as well as their power. For gamma oscillations, changes in the power of brainwave activity are called evoked when linked to a provocative stimulus and when they persist within the first 120 milliseconds after the start of the stimulus. The evoked gamma is thought to represent the processing of information within a confined cortical field. In contrast, the gamma oscillations of the so-called induced component represents the processing of information across neural networks in different cortical regions. This component of gamma activity, the induced, has a variable onset, that is, one that is not locked to the stimulus, and usually begins around 240 milliseconds after the stimulus. Gamma oscillations are usually measured in association with provocative stimuli, the most common being figures of illusory or subjective contours, the so-called Canisa figures, which evoke the percept of a shape produce gamma oscillations during visual cognitive tasks. In autism, EEG recordings when presented to the patient with a Canisa figure have shown an overall increase in gamma oscillations compared to neurotypical subjects. These findings have been interpreted as reflecting a reduction in the signal to noise ratio caused by a decrease in inhibition or by a reduction in the total number of PV positive cells. In our TMS studies, we have therefore used Canisa figures to elicit gamma oscillations to clinically follow our patients and gauge how they are doing, especially when complemented with behavioral screening techniques. Faraday's law of electromagnetic induction, or simply Faraday's law, states that the voltage induced in a closed circuit is directly proportional to the speed of change of a magnetic field. In transcranial magnetic stimulation, or TMS, a capacitor bank is quickly discharged to create a controlled pulse of a very high current through a conductor. This current is as high as 10,000 amps. Capacitors are used to store energy and are efficient for discharging short pulses or bursts of current. When the conductor is wrapped to form a coil, the magnetic field of each turn of wire is added with those of its neighbors. The resulting magnetic field has polarity, with a north pole and one with a south pole at the other end of the coil. When a conductive material is added to the center of the coil, this helps to concentrate the magnetic flux in a well-defined and predictable field. In TMS, the magnetic field that arises from the coil varies between 1.5 and 2.0 Tesla, which is approximately the same as the magnetic field intensity produced by the MRI equipment used in radiology. At low frequencies, and by this I mean less than 1 Hertz or 1 cycle per second, TMS has an inhibitory effect. This effect may be due to its action on interneurons. Some of these inhibitory neurons have a geometric orientation more favorable to the magnetic field lines produced by the coil, which induces currents along the axon rather than through them. When higher frequencies are used, and by that I mean more than 5 Hertz, all of the neurons within a cortical area are stimulated. That is, they are stimulated regardless of their geometric orientation. Because pyramidal cells comprise 70 to 90% of all neurons in the cerebral cortex, the end result is that TMS becomes excitatory at higher frequencies. In TMS, the influence of the magnetic field is restricted to a small area within the surface layers of the cerebral cortex, approximately 3 centimeters squares, slightly bigger than the size of a quarter. Therefore, it is important to select an appropriate area or region of interest to maximize the effectiveness of the intervention. Among the many areas of the cerebral cortex, the dorsolateral prefrontal cortex has been closely related to abnormal functioning in patients with ASD. This prefrontal cortical region is involved in the genesis of executive functions, including, as seen in the slide, playing an important role in cognitive control, participating in supervisory care, synchronizing thought and action according to internal objectives, and providing signals to other brain structures to guide the flow of activity along neural pathways. In addition, this area is responsible for the inability to inhibit inappropriate behaviors that limit possible adaptive responses. Because the prefrontal cortex is widely interconnected with other areas of the cortex, correcting this function or the function of this region could help normalize the function of its multiple interconnections across the entire brain. This is what I would call a therapeutic cascade. In general, the parameters of our TMS studies have used a coil in the form of the number 8 with low frequency stimulation, meaning less than 1 Hertz. As I explained previously, this low frequency stimulation has an inhibitory effect on the cortex. Because of its connectivity and role in executive functions, we have opted to stimulate the dorsolateral prefrontal cortex. Most studies so far have excluded patients with seizures or brain trauma. Participation has been limited to high-functioning individuals defined by an IQ of more than 70 and an age range of 8 to 18 years. Outcome measures have included gamma oscillations, event-related potentials, behavioral examinations, and autonomic measurements. In our studies, we thought that the best control group would be a number of autistic individuals and with similarities in their IQ and socioeconomic level, as well as matched by age and sex, and who were not subjected to TMS treatment. After completing the study, participants in the control group were offered active treatment. In total, we have done about 15 clinical trials of TMS in ASD, recruiting several hundred patients, maybe thousands. In this slide, we illustrate the study design of one of these clinical trials. It began by recruiting and screening 124 patients who were divided into different treatment groups. The control group was formed by a similar number of autistic individuals paired by age and gender who did not receive active treatment. The study required about 2,000 clinical visits, not counting those visits necessary for the patient to get used to the laboratory. The study design in this slide emphasizes the time and work required to perform each of these studies and why TMS studies take so long. So we proceed with baby steps. Our results indicate that in autism, the evoked gamma activity does not discriminate between types of stimulus, while in controls, the early differences in gamma power between target and non-target of the Canisa figure are significant. These differences are normalized after treatment with TMS, and you can see the slide at the upper right. In order to explain to all listeners the clinical significance of the results or how they help explain some of the symptoms of autism, I would have to say that in the brains of some autistic individuals, networks of overactivated and noisy neurons impair cortical connectivity between different regions of the brain. This makes it difficult for the autistic individual to selectively process the salience of any particular information based on its relevance. In this regard, a face, a flower in a vase, a house, or a dog can all have the same relevance to an autistic individual. We believe that this explanation is correct, as in other studies, our group has shown that TMS therapy results in greater coherence of function between distant brain regions, indicated here in the lower figure, right side of the slide. This improvement results in a direct relation to the number of TMS sessions. Task monitoring is an executive function. Being able to follow a task involves focusing on the task in question, remembering and following multi-step instructions, being able to detect errors, and instituting corrective behaviors when these errors are noticed. The ability to institute corrective actions allows people to avoid making more mistakes and helps them adapt to challenging environments. It is for these reasons that the first studies of our group on TMS in autism focus on executive functions that had to do with monitoring and correcting errors. The study presented in this slide was one involving 28 individuals, 14 each for the ASD and control groups. The active group received 12 sessions of low-frequency bilateral TMS on the prefrontal cortex. Results in ASD patients receiving TMS showed significant improvements in error detection and correction. These results suggest that the treatment with a TMS in ASD may improve executive functions related to error monitoring. More than anything, the study emphasizes that TMS therapy can change one of the central deficits of autism, namely improving its executive functions. Now, if you remember one of our first slides, the one with Declan Murphy, I can say that with TMS, we're moving away from the symptomatic treatments to interventions that target some of the core pathology of autism and are therefore able to normalize some of its more disabling features, as in the case of executive dysfunction. As a note, we have subsequently reproduced these results in several other published clinical trials. This slide demonstrates the effects of an increasing number of sessions with TMS on the error rate and post-error response time. It indicates an improvement that correlates directly with the number of treatments. The delay that is observed after making a mistake is a recovery strategy that helps maintain control over a task and tries to avoid future behavioral failures. In autism, this delay is significantly shorter prior to treatment with TMS, indicating a propensity to take repetitive actions without thinking about it impulsively. After TMS, this time is prolonged to within the normal range of values. This task has been of clinical importance when we follow a particular subtype of ASD patient, namely those patients suffering from impulsivity or other characteristics of an attention deficit hyperactivity disorder. This is a screen photograph of one of my favorite oscilloscopes that has as part of its research tools the ability to analyze recorded frequencies. The upper channel shows a wave that mimics an EKG. The x-axis represents time and the y-axis is the amplitude of the voltage. The plot comes from an arbitrary waveform generator, not a real EKG. The upper channel allows us to study linear parameters in the EKG that can be discerned in the time domain, such as heart rate and its variability. The bottom channel illustrates the frequency analysis of the previous tracing. In this lower channel, the x-axis is the frequency and the y-axis is its power. In the frequency spectrum shown, we can arbitrarily divide the tracing into high and low frequency components. Spectral heart rate analysis represents a measure commonly used in psychopathological research to evaluate autonomous cardiac control. Attenuation in the power of the high frequency component is sometimes taken as a parasympathetic control index and also as an indicator of limited psychophysiological flexibility. In autism, we have found deficits in modulating the high frequency range in different social tasks. At a baseline, our samples of autistic individuals usually have increased sympathetic activity, as shown by their heart rate, upper channel, and a diminution of their parasympathetic tone, as shown in the attenuation of high frequency components of the EKG, lower channel of this recording. In several clinical trials, our group has shown that the application of low-frequency TMS to the prefrontal cortex of autistic individuals normalizes parameters of the autonomic nervous system with an additive effect observed with increasing number of treatment sessions. This takes advantage of the fact that the prefrontal cortex affects control over the limbic regions of the brain. The results of the interventions are manifested as a reduction in heart rate, seen in this slide, as an increase in the EKG's RR interval, and as an increase in heart rate variability, seen in the slide as an increase in the standard deviation of the RR interval. We hope that this intervention will serve as prophylactic in preventing sudden cardiac death and to treat the dysautonomic symptoms commonly seen in autism. Our results suggest that autonomous activation measures, as well as autonomous cardiac regulation profiles, could be useful in distinguishing certain subgroups of autistic individuals and how we treat them. In different articles, our group has shown that TMS therapy provides behavioral improvement in terms of repetitive and aberrant behaviors. These behaviors are what we often see as manifestations of anxiety in this patient population. we're also very interested in following many of our patients' comments that with TMS therapy, they have noticed improvements in sleep disorders as well as in gastrointestinal symptoms. These behavioral improvements are related to the number of TMS sessions. The higher the number, the better the behavioral response. This type of therapy has to be investigated as an alternative to the use of neuroleptics for the treatment of poorly adaptive behaviors. At present, TMS therapy has few side effects, while pharmacological interventions, for example, neuroleptics, leads to a plethora of side effects such as weight gain, constipation, and drowsiness in many of the children receiving them. Our group has also examined possible synergism by combining the use of TMS with neurofeedback. Our studies have measured executive functions and behavioral measures. The results of our clinical trials have shown synergistic improvements that are very significant for executive function, positive changes in EEG results, and an increase in the relative amplitude or power of gamma activity. Before ending this lecture, I would like to provide a warning note. A recently published book and a bestseller entitled Switched On and written by John Elder Robinson has idealized the treatment of TMS as a possible cure for autism. In the book, it is said how John substantially and permanently improved his empathy and emotional understanding abilities due to this therapy. After his first therapy, John tells us that while traveling home, he placed a tape inside his vehicle recorder, and for the first time in his life, the music caused an emotional reaction in him. John participated in several Harvard University studies. None of them were clinical trials, and they used individual or single TMS pulses to investigate brain functions. Single pulses have no discernible effects beyond the stimulation session. Despite the conviction ingrained in John's narrative, we cannot claim that the effect of the therapy went further than that provided by a placebo effect in this particular case. In finalizing this lecture, I would like to emphasize a point. Transcranial magnetic stimulation remains an experimental intervention in the field of autism today. No multi-center trials have been conducted with a large enough number of participants to test their effectiveness and allow comparisons with other treatments. Likewise, participants who receive TMS for autism have not been followed for a considerable period of time, and we do not know how long some of its positive effects last. So far, the US Food and Drug Administration, the FDA, has not recognized the therapeutic value of TMS in autism. Those interested in obtaining more information can do so by reading some of our recently published books, Defining Autism or Autism Updated. Autism Updated was an attempt I made to answer all the questions about autism that patients brought me to my practice. You can also follow us through our blogs, scienceoveracopa.com, that's my wife, or mine, corticalchauvinism.com. You can also write to me through the comment sections of my blog. Thank you so very, very much for your kind attention and patience. I hope that this little introduction to our research has been to your liking. Thank you.
All right, well, thank you, Dr. Casanova, for that presentation. My name is Denise Fulton, and I work for ARI. I wonder, we've got a little time left if you have time to answer just a few questions.
Please.
We did receive many questions, so if your question is not asked during this period, Dr. Casanova has provided his email address, so I'm going to invite people to send, especially if it's a more detailed question, if you could send those to him directly. I'm sure he'll be happy to help. So the first question that I wanted to ask about is catatonia related to autism, and if any of the TMS work or studies revealed anything about a relationship between TMS and improvement in catatonia.
Yes, there haven't been any studies that I know of in regards to TMS and catatonia. The therapy that is usually applied to catatonia, usually first of all, are benzodiazepines, and if they don't work, you can try electroconvulsive therapy, which is very different from TMS. Electroconvulsive therapy may actually use pulse currents, but of a much higher power than TMS. And the purpose is to actually provoke a seizure, which is what we are trying to avoid in many of our patients because they have a predisposition to seizures. So TMS hasn't been used for this purpose. Maybe it could be an idea to do so under a very controlled setting, but the studies have not been done as of present. It's ECT what has been used, not TMS.
All right, and I know that you don't work for an insurance company, but we did get the question several times about insurance coverage for TMS. Are you aware of any plans that cover this for autism or for other issues that people may be experiencing?
No, the answer would be most probably it's not covered, primarily because it's not approved by the FDA as a treatment per se. It still remains as a research endeavor, so it would not be covered by insurance companies. This has actually caused that some of the people in private practice who are using TMS, they charge bundles to patients that come to their practice. And I have heard other stories about patients that have spent $20,000, $50,000 in treatments from centers who really do not report their findings. They really do not publish their results in the literature. They are not peer-reviewed articles or being monitored by the IRB of any institutions. So I would say that until that happens, I would tell people that if they are interested on participating, do so under a research basis, to go to clinicaltrials.gov and look under the words TMS and also autism and see if there are any clinical trials available near you.
All right, you touched a little bit on how there's the possibility of a synergistic effect between neurofeedback and TMS. Can you talk a little bit about what the difference is between neurofeedback and TMS? That was a question we had several people ask.
Okay. Well, in neurofeedback, a patient, and I will give you an example of what we do in our laboratory, he sees a screen on the laptop that portrays his wave patterns, brain waves in real time. And he tries to control the same. It's something that he has to learn on his own. And you can modulate those brain waves. The idea is that different bandwidth of brain waves, they correlate with different behaviors. When they are very slow, you have somebody who's sleepy. When you have higher frequency waves, you have somebody that is awake. When you have very high frequency waves, primarily in terms of gamma, that is when you actually concentrate, when you exert mental effort, when you are participating in joint attention or executive tasks. And that's the part of the brainwave bandwidth of the spectrum that is primarily altered in autism, okay? So that's what neurofeedback actually does. The mechanism per se in terms of the neurons and the neurotransmitters, they haven't been worked out. With TMS, you get a pulse, a magnetic pulse from a coil, when you pass a current through it. And if you have a conductor, in the case of the cerebral cortex, if you have some axons nearby, it will induce current through them. The two mechanisms appear to be completely different, but they offer synergism to each other, especially in regards to gamma activities. I must also add that one of the other peculiarities that I wanted to pursue was also the use of CBD oils, marijuana. And that's because they also act through a different receptor, but on the same cells, on the basket cells, on the parvalbumin positive cells. So I do believe that by combining CBD oils with TMS and neurofeedback, we will have even greater synergism.
Okay, so you talked a bit about the positive results that individuals have had. Can you talk a little bit about people who didn't have a great experience with TMS, or the individuals who didn't respond as positively?
Mm-hmm. Well, we have had 2 individuals that actually dropped out of our studies. They were for idiosyncratic reasons. One of them actually was a track runner, and he actually tumbled over his own feet while running, and he blamed the TMS stimulation that he had received before, I think the day before. Otherwise, most of the people that drop out of the study, like in the sample that I illustrated in one of my last slides, where we had 124 patients that came in, and maybe we had like 112 when we finished. They were all due primarily to people that were outside of our geographical location, and they had to travel a lot. One of the persons had to travel like 3.5 hours each way, okay, back and forth 7 hours. So they couldn't keep up with the 18 hours, 18 sessions of studies. Otherwise, the major side effects of the technique are evoking seizures, which is an extremely small percentage, and only if you use high frequency stimulations, which we don't. The FDA has actually posted security warnings claiming the safety of TMS for very low frequency stimulations. It also provides for headaches because when you provide the magnetic impulse to the cerebral cortex, it actually passes through all of the external layers, which includes muscles outside of the skull. And that causes them to contract back and forth, which repeatedly, when done repeatedly, it provides tension type of headache. It can be treated easily with a couple of aspirins, and people usually adapt to the same in 3 sessions. And the other one is just noise because of the clicking, loud clicking of the equipment. And if patients desire so, we can provide for earplugs. So just to answer the question, overall, there haven't been major side effects, at least based on our experience.
Well, I'd like to thank Manny again for his excellent talk. This is probably the 3rd or 4th time I've heard your lecture on TMS, and each time I learn a lot more, and it makes me think a lot more as well. So thank you again.
Thank you, Steve.
Yeah, it is so much better when you explain it to me. When I try and read it in the books, I have problems and I get lost. But when you explain it, then it's much easier. Thank you. Thanks for a great presentation.
Thank you. It has been quite humbling for me to be here on this first conjoined presentation. The 2 organizations, the World Autism Organization and ARI, are exemplars for me and for many other individuals in the field. So it has been a great honor.
Thank you.
Bye, everyone. Thank you for attending.